It's my great pleasure today here to introduce our speaker, Dr. Bingjie Wang. So Bingjie got her bachelor degrees in both physics and philosophy from University of Pittsburgh, and then she moved on to Johns Hopkins to get her PhD degree, where we both worked with Professor Tim Heckman and overlapped for a brief period of time. And Bingjie then moved on to the Penn State University as an assistant research professor, working with Professor John Lydia. So without saying that, Bingjie is an expert in one of the most popular SAT model code, the post vector, while she has applied this code to straining James Webb data to cell populations from Galaxies at the earliest universe. So Bingjie is currently a Hubble Fellow at Princeton University, where she will keep exploring parameter space and models that describes galaxy formation and evolution. So that's all. Stay tuned to Bingjie's upcoming work, and we're excited for today's topic.
Thank you. Thank you for a nice introduction. It's also nice to talk to many of you throughout the day. This is my first time in the state of Texas. Pleasantly surprised by the weather. Not a good idea to come in the summer, but it's a nice refreshing period from the freezing cold in Princeton. Okay, so today I will talk to you about some of my recent works with the James Webb Space Telescope, particularly at the high redshift frontier. So without further ado, let me start with a bit of the background. I started my graduate school actually doing CMB cosmology, so I always like to start a slide on this just to show how much we know about the universe as a whole. We actually have a pretty good story about how the universe evolved. It started with Big Bang. Now, as we're looking at the CMB, which is the surface of that scattering, the outer group of Big Bang. The age of universe is only like 400,000 years here. And then it just goes through the dark ages where nothing really happened. And then at some point, the first stars and galaxies started to form, and they started to ionize the gas around them. And at some point, the universe just became fully ionized as it was currently now. We see this beautiful local universe where we see these diverse galaxies. Now, to map large-scale structures from the beginning to the local universe, we have a pretty good story because the dark matter, even though we don't know what they are, they only interact gravitationally. So we can simulate them very well on the large-scale structure. But the baryon physics or no matters are difficult. The baryon physics are just complicated, and to really understand how the universe evolved from those states to the diverse and beautiful galaxies observed today, there's many open questions. And one way to answer them, and perhaps the only way, is to take the very deep images of the sky. This is the Hubble Deep Field. It's perhaps fair to say that nothing has revolutionized extragalactic astronomy as much as the Hubble Deep Field. When Hubble just launched, there was widespread skepticism about whether we can really see the distant galaxies, as it was some of people thought. Then the direct space telescope, and then steered the telescope like for an outrageous 10 days. And then the result is this iconic image. Every point here is a little tiny distant galaxy. So this really changed our perception of doing extragalactic astronomy, that we can really look directly into the image of the distant universe. Now known as the Gen Z11, was a record holder for the highest redshift galaxy ever identified. This is in the Hubble field for a long time. This is very unusual for this high redshift field. What you're looking here is the HST image of it. It's like it's a fuzzy ball. What occurred is this is the image from Webb. Immediately we see the resolution power of Webb, right? You go from here to here. So and the redshift is confirmed now at redshift 10.6. Okay, so now since we're talking about Webb, let me just give you some information on the Webb telescope. For comparison, this is the primary mirror of Hubble, and here we have the primary mirror of Webb. This is the most expensive telescope ever built. I did my PhD at Hopkins Space Telescope, which is operation center of Webb and Hubble. I just directly across the street, so I hear all those talks and stories. But it just been delayed for so many years, and it was very exciting to see it finally launched. And when it's really unfolded, it's gonna larger than a tennis court, and now it's orbiting around many miles away from us. The exciting part of Webb not only is this resolution power gained by this enormous increase in the size of primary mirror, and more is about the wavelength range it probe. So it looks into the infrared. If we put into a timeline, then Webb really opens up the frontier where we can probe deep into the epoch reionization and see the distant universe, which is not accessible with Hubble or the ground-based telescopes. Those are just a few of the questions I'm particularly interested in. Then how the first stars form, the first galaxy, the first black holes, and of course, most importantly is what should we be asking? A lot of the most influential or impactful discoveries on Webb was not even listed in initial proposals. So this is also starting to become true in the Webb era. And in the later part of talk, I will talk to you about some of the most surprising findings come out of Webb, the little red dots. All right. So here I'm showing one of the WebD fields. This is the ABEL 2744 cluster field. It's come from one of the Cycle 1 treasury program called Uncover. It's also a program that I've been very deeply involved with. It's a tiny little field. But because of this boost of gravitational lens, we just get this again efficiency in the exposure time. So in this tiny field, you're looking at about 100,000 galaxies in this tiny 10 arc minutes squared field. What I was mainly responsible for is to turning this beautiful image into even more beautiful parameters. Which is the distance, stellar mass, gas and dust contact, and those are the physical parameters we really need to, say, do galaxy formation and evolution studies. Just to provide you with a bit more context, since my expertise is in distant galaxies, so the challenge of doing distant galaxies, I can show you in one slide, is this is the Milky Way. Right, we see those beautiful structures, the central black hole, the bulge. There's different components like the star-forming regions, dust, and molecular cloud. But if for distant galaxy, the field I'm working, what you see is this. It's a little dot. That's all the component in this crammed into this one data point. Of course, we sample across the wavelength band, but still, a lot of the information it just now in this tiny data. And I will show you later, sometimes we also see those like just like a point source. The structure is the point square function of Webb. You can imagine when we cramp this so much into this tiny dot, then the brightest source will dominate the total light output. Then what we're trying to do is to infer, say, the star formation histories of the stellar mass. But then it's the problem of how we infer the fainter, older stellar populations when the young populations of the central black holes just dominate the total light output. And to infer the star formation histories is like inferring from the present light. So you see, it's very challenging. On the one hand, we have devoted enormous effort and investment into building those flagship observatories and getting those data, but this problem means it's also worth spending time to think about the models. Because we are not in the likelihood dominated region, the models we put into the inference has a huge impact on the result of the inference. So just to take a step back of what I mean by stellar population inference, and usually this is the image we have in mind. So there are different components goes into the stellar population models. First, we have those data. I'm just showing you those are photometric points sampled on some spectrum of a galaxy. And on the other hand, we have those fold models, basically the stellar libraries isochrones, where given the say, stellar mass or star formation histories, we can predict what the light or the spectrum look like. And in the middle, we have the priors. This is what I mean. It's worth to think about models because we're not in the likelihood density region. This prior actually has a huge impact on the data, on the inference. Now, this is the Bayesian formula that we all know and liked. What we want is a posterior of all those beautiful star formation histories or stellar mass. Okay, so I will just emphasize this point further, which is the importance of the priors. I spent a fair bit of time trying to think about how to make the whole inference, especially in the Webb era, more robust by putting some galaxy evolutionary priors. So it's purely observational driven. The idea, I won't go into detail how I built those priors, but the idea is fairly simple. We think the observed universe is our sort of a good representation of we have the knowledge of what's the observable universe, and then I want to put what we learned from those state-of-the-art observations back into inference pipeline, and just to make the whole inference more robust. So those three priors are public and part of perspective. Here, just a mass prior basically tells you, well, at lower mass, we expect more galaxies. This is well determined from stellar mass functions. Here, there's a number density. It basically just we expect to see more galaxies when it's more closer by. Here, just star formation rate is function of time of the universe. It's matched to the cosmic star formation rate density. Basically, just reflects the global star formation history. There's more star formation in the early universe and less star formation in the local universe. So, does this really work? We can test it on real data, right? So I'm showing one example. This is a quiescent galaxy candidate. So from photometry, what we're looking at those big Balmer bricks. This is indication that the galaxy there's no star formation. We call it the quiescent galaxy. This is a photometry. So this is one of the robust candidates from an earlier Webb paper. Then in the later paper, a student, so we refitted the same data. But the only change is we put in those galaxy evolutionary priors. But we infer those star formation histories. So those emission lines are indications that the galaxy is not dead, but instead they are star formation activities. Sorry, I switched from F lambda to F nu, but the point is there we infer star formations. Well, what's about the grand truth? We can take spectrum of the galaxies, and then we can really tell whether it's a dead galaxy or not. Later in the year, we have a follow-up spectrum of this galaxy. This is a spectrum of this. We see those emission lines, right? So this tells you it's certainly not a dead galaxy. So this is an example showing how much we can be more robust about the inference if we just put in more physics into the whole inference pipeline. Right. And we subsequently used this model to turn the deep field, this is uncovered deep field, into a stellar population catalog. The data and the scripts are all public. Here I'm just showing you a flavor of the parameter space surveyed by this program. This is stellar mass as a function of redshift. We're really pushing down to the low redshift region. And also you see this wide dynamic range prompt by the survey. Okay, so this is the data from Uncover. We have all the broadband photometry. And later we have a cycle 2 program called median bands, which basically give you, we sampled all the median bands. So the total data set is very exquisite now. So it's a 20-something band, broad plus median, a full photometric coverage of this about 2744. And it really sets the standard of the extragalactic field. What's next? Well, we have pleasant surprise that this program got approved. There's a cycle 4 treasury program. It will take like a little bit 200 hours in primary orbit and a couple of 100 hours in the parallel to take all the median bands in 4 legacy fields. So those are all candles fields. I'm not doing the stellar population models, but the framework is gonna be the same. So we'll have very consistent modeling process across all those fields. And this, I think, is the largest extragalactic data sets the challenge is the data volume, but all the modeling part, we will test it out. Okay, so the data is coming in. We'll see if we can find more interesting things in those legacy fields. Okay, yeah, and the special thing about Uncover is that it's a two-part program. So we first take the image, and then after half a year, we just take spectroscopic follow-up in the same cycle. So in cycle 1, we have a lot of spectroscopic follow-up building on those photometric and stellar population catalogs. We have a lot of interesting papers coming out of the program, but here I just want to show the paper that I led, which is the highest spectroscopic confirmations of the galaxies. Here we are looking at this is Uncover Z12, which is redshift 12.4, and the other is at redshift 13.1. At the time of writing, those are like the second and fourth most distant galaxies we have observed, but this is cycle 1. You can see this redshift record has been broken again and again when we take more data, especially with the GTO team. There are a couple of interesting things about them. First is they are very luminous. That's why we can detect them with a shallow spectroscopic follow-up, and we can see a very good sharp Lyman break to pin down the redshift. And the other interesting about them is their size. So if we just focus on the redshift 12.1, we see like it's extended, right? The lensing magnification is less than 2. So this is not purely due to the shear or due to the lens, but really the intrinsic shape of the galaxy is much larger than we expected. This is especially true when we compare to other high redshift galaxies at comparable redshift. Say those Jades galaxies, they look just like a tiny little blue dot on the sky, very much different from those a couple hundred parsec in size. Maybe this is just some scatters in the mass-size relationship. We don't quite know, but yeah, it's interesting properties of those galaxies we discover in the Uncover field. Okay, since now I think that this record recording broke again and again. This is one of the surprising things in Webb is those very luminous UV bright galaxies, right? We have this redshift 12.5, and I think this is the current record holder at the redshift 14. But at the same time, we also see those galaxies appear to be napping in the early universe, which is they have this star formation rate sort of comes down a little bit at high redshift, but not quite that. But there's such a high redshift, we don't expect them to be permanently quenched. But at some point, they may the star formation may be back again. There is actually one unifying nice explanations to explain both the very luminous high redshift galaxies and those napping galaxies at a moderately lower redshift is this bursty star formation model. So what is bursty star formation? Here I'm just showing example from a fire simulation. This is a specific star formation rate as a function of time. The exact unit does not quite matter. I want to show you this up and down in the star formation history. So at some period it has high rates of star formation, and at some places it shuts down temporarily. So you can imagine for those very high luminosity of those high redshift galaxies, we probably just catch them in this high rates of star formation phase, the bursting phase. And for those mini quenched or napping galaxies, we will just eventually catch at this sort of down phase. So this is a nice unifying explanations. However, the unnatural question is, can we really constrain the burstiness in those galaxy populations? Well, as I talked at the beginning, we have those state-of-the-art stellar population models, those SCD-50 models. Can we do that to infer star formation histories? Well, okay, we can do some very simple model tests. So here I'm simulating a high significant noise spectrum. In black, that is the simulated spectrum, and in purple is a best fit model spectrum. It's perfect fit. We can match the data at like 1% level. What does star formation history look like? Well, this is a star versus look back time. The true star formation, we put in a very simple one so that we can have very direct or quantitative test of how well we recovered star formation rate. The truth is here, you see it's up and down, up and down. But this is what we inferred from data. Even though the data is perfect fit, we do not see the burst star formation. Okay. Well, the prior we put in is a continuity prior, meaning it disfavors those large changes in different beings. Then we can ask, well, what if we tell the model that we expect large changes in different beings? Can we recover the bursty star formation? And here's the result. It's very happy to put a lot of star formation in the recent time, but not much. There's no star formation in the older time. This is a classic outshining problem because the young stars are just so bright and they dominate the total light. So the models, when we allow more variations in the star formation histories, they just give a single burst, but we just do not correctly infer the burst or the duty cycles. The problem is really there's a mismatch between the complexities of those burst star formations and the information content just in those individual galaxies. It's just really hard to infer the complex behaviors just by single galaxies. Okay, this may seem hopeless. Well, then is there other ways to get constraints on bursty star formation? What if we look at groups of galaxies instead? Because the idea is, well, if we somehow can group the galaxies, and then maybe we're just observing different phases of these bursty cycles, then in principle, there are more informations in the distributions of group galaxies, and then we maybe can get more or constrain better the bursty star formation. So this is just a conceptual illustrations of how this works. So we have different star formation histories. So they have different amplitudes and also different duty cycles. And then we can simulate the model spectrum given a different star formation history. And we see the different timescales and amplitudes would give you observably different spectral features. Say, look at this is far UV, near UV. Those are a bunch of Balmer emission lines, and this is the Balmer break, which traces the oldest star populations. So those tracers are sensitive to different timescales, and in each of those models, they produce different spectral features. Now, what if we group them? This is a distribution of galaxies of a galaxy that has the same hyperparameters in bursty star formation, meaning they share the same timescale and amplitudes in burstiness. And we can simulate a bunch of different galaxies, assuming the single same population star formation models. And this is the result. So we see the actual axis doesn't really matter. The takeaway message is they produce different distributions. So the idea is even if the information content in each of the single galaxies is not enough to constrain the complex behaviors in star formation history, by looking at a group of galaxies, the distributions of the spectral features, we can constrain the burstiness in those early galaxies.
Are you talking about literal physical groups or just all galaxies you find they're at some specific redshift range, or what do you mean by group here?
Oh yeah, observationally, I mean we group by the narrow redshift being and also by mass. Okay. Because the idea is they have to share a similar sort of bursty cycles so that we can get meaningful constraints by grouping them. Yeah. So that's one challenge to go from this concept to observation.
The mass is something that you want to infer.
Right, exactly. Yes. So this is like a proof of concept sort of paper. And I have a grad student at Penn State have been working with me trying to turn this proof of concept into a full working pipeline. This is technically very challenging. I'm just showing this is madness, but I just want to show you it's durable. And we use some, we need to leverage some machine learning technique called simulation-based inference because the conventional way of doing this is just way too slow. But it's very promising. So I just want to show you an example. This is the result of inference. So what x-axis is called the power spectrum density. Basically, it's a Fourier transform of the star formation history. Basically, tell you how much power is in there. It doesn't really matter. These time scales. What I want to show here is this is what it inferred if we input a fire like with very bursty star formation histories. And this is what those illustrates like, not so bursty star formation history look like on this plan. And the inference can really tell apart those two very different scenarios. This means we finally have a way to falsify those very different feedback models. This is the different simulations usually predict very different. They input different physics and also have different predictions on the bursty star formation. But now observationally, it's very possible that we can falsify those models. So I'm very excited about this.
Does Illustris have the time resolution to constrain those very short timescales?
No, that's why we call Illustris like PSD. We have to make something to get the time resolution. But the point is they are very different. The fire is a very bursty one, but Illustris is not so bursty. Okay. Okay. So with that, just now imagine we can have some constraints on the burstiness. What can we do as a step further? I didn't just write a paper saying SCD field does not work, but there's a positive message at the end of this paper, which is, well, if we have some constraint or understanding on the burstiness amplitude or time scales, so we can use this as informative priors and then put it back into the inference to see if we can get improvement in the mass estimate or the star formation history estimate. This is the result. So this is simulated spectron overplotting in purple is the best fit. This is the true input. Overplotting in purple is the recovered star formation history. The only change between this much better recovery versus the much worse recovery I showed earlier that in here we put in an informative prior on the bursty star formation, and this is a lot. So this is a very promising way to solve our shine. Basically, we can not only get the recent burst, but also at much further back in look-back time. Okay, great. So that's one sort of exciting things about Webb is those bursty star formation histories, but maybe you're all waiting for it, the little red dots. This is, in my opinion, the most exciting discoveries coming out of James Webb. So in the second half of time left, I will just switch the focus to the little red dots. Let's get right to it. In Webb's first month, people quickly pick up those little things in the public fields. In the initial papers, we interpret it as stellar populations. What is it? Nature paper, so something's wrong with it, as you know. But just to provide some context, why we think those are exciting is if we just say they are pure starlight, then what's the stellar mass and how it's compared to the normal populations? Well, this is stellar mass, and this is a redshift. Those are just other sources within the Webb field. Those are our little red dots. Even more context, this is a mass of Milky Way, but Milky Way has a lot of time to involve in this stellar mass, right? But this is a universe where we are concerned. It's only like 500 million years old. It may sound like a long time, but it's only 3% of current age. So it doesn't really make sense to find such massive galaxies at this early age. And this is really what draws people's attention in those sources. And as we have more data from Webb, we started to find more of those little red dots. They seem to appear in every pointing in Webb. So the implied number density, even though the selection criteria varies, are very high. That means whatever they are, they play a very important role in this evolution of early galaxies and black holes. And if that does not convince you they are important, now it is officially a keyword in APT. Little red dots. It's with those other noble catalogs like AGL host galaxies, galaxies. Yeah, I was writing 2 proposals in the Hubble Fellowship Symposium, which has a perfect time, just 1 week before the Webb deadline. Like, great job, Space Telescope. So yeah, and in those early studies, we not only have images of them, for some subsamples, we also have 60th spectroscopy, which is just basically we have a snapshot of the alpha lines. This is just showing you some of those. This is, they are very broad, right? In the standard considerations, those broad lines are always almost exclusively associated with a supermassive black hole, because you are just basically seeing gas spinning at a really fast speed around the black hole, and that's what gives you those huge velocity dispersions. All right, so are they just black holes? That will certainly solve a problem that we are seeing over massive galaxies in early universe. What we really need is a full spectrum of those little red dots to maybe understand their nature. Now, just in March 2024, we finally have a near-spec spectroscopy of one of the earliest, or some of the earliest and brightest little red dots. This is a paper that I led coming from the RUBIES program. I'm just showing you one of the examples. This is Princeton spectrum. This is just the cutout of this. What's the first thing one will notice? Well, those large H-alpha lines, those very broad H-alpha lines are really hard to miss. So this is highly indicative that we are seeing gas just accreting at a very high speed around the supermassive black hole. However, there turns out to be a more exciting half of the story, which is those spectral breaks. This is usually associated with the Balmer break of involved stellar populations. So just I will show more examples later, but the confusing part of seeing this spectrum is that we seem to have confirmed all hypotheses at once. We see bright emission lines suggest of AGN, and those breaks suggest of old starlight. Well, it was pretty difficult to convince all my cohorts that we're really seeing the Balmer break. So let me just show you a zooming around the Balmer break region. This is, we have 3 little red dots at this redshift. So I just stack them. It's a simple median. What you see in black is the simple median of the sample. You see it all shares similar shapes and all break at the same place, which is a Balmer limit. More importantly, we can compare it to models. So on top of it, in red, I'm showing the best fit galaxy spectrum. It's also averaged over the 3 samples. So it lies on top of the observed black lines, meaning the models can also properly interpret this break as a Balmer break from stars. Now, this is really surprising because Balmer breaks are produced by hydrogen absorption in the atmosphere of warm old stars. They are typically only visible in stellar populations after star formation, like really shut down for over 100 million years or something. So we are looking at really old stellar populations. But the age of universe at this redshift is only 600 to 800 million years, giving very little time to form those involved stellar populations. All right, so we are seeing broad Balmer lines and also those Balmer breaks. Then how do we interpret this data? In the papers, we put in a set of different priors favoring different galaxy to AGN contributions, just to see whether the data are informative enough to decompose the AGN galaxy light. I'm showing just one example of the model fit from bottom to top. We just have increasing stellar contributions to the total light. Those are all statistically equivalent solutions, meaning that it's really hard for data to tell whether we're definitely seeing AGN versus stellar light. But each of those would have drastic different implications on how we think those are and the broader implications to galaxy formation or early galaxy formation as a whole. I would just spend a few more minutes on the interpretations of those different models. So let me start with the simplest one, which is this galaxy only fit. This is the simplest thing we can do. Just fit the whole thing with a standard stellar population model. In blue, this is the best fit spectrum. You see, it just fits data really well. The interesting part is the star formation history. So you see, it really accumulates a lot of star formation at the very early universe, and then it shuts down. Right? This sharp decrease is what needed to predict this sharp break. Now I mentioned this star formation history because it has an interesting connection to one of the other surprising findings from Webb, which is this massive quiescent galaxies at redshift 5-ish. So what I'm showing here, this is a cutoff of one of those high redshift quiescent galaxies. This is a star formation history of this galaxy. The interesting of this is that it has accumulated a lot of mass at redshift 8. This implies unusually early and efficient star formation. It's very challenging. So we look at those big box simulations. It's really hard to simulate those massive quiescent galaxies. Now, the interesting happens is what we overplot the star formation histories of those little red dots, assuming a pure galaxy fit. This is what we have. The exact shape is different because the bindings are different, but that doesn't matter. This is the only model, it turns out, that can produce a sufficient star formation in this early universe to match the quiescent galaxies. Now, this is important because if those star formation histories inferred for those quiescent galaxies are correct, the fact that they are forming so many stars at redshift above 8, meaning their progenitors should be very bright. But we have not found any of their progenitors. In other words, we're missing a critical evolutionary link in this quiescent galaxy. But if we buy into this interpretation that little red dots are just compact galaxies, then we can draw an elegant narrative that is those are the progenitors of those quiescent galaxies. Well, do I really believe they are? Not really, but it's just a very elegant explanation. So, but this has come about many problems. I will just emphasize one of the most critical ones, perhaps. That is, the inferred star formation histories, assuming a pure galaxy-like scenarios, is uncomfortably early and efficient. If you're not familiar with those Epsilon plots, all we care is this purple line. This is the stringent theoretical upper limit, meaning all the baryons in the early halos are converted into stars. So everything above this line is a forbidden zone. And this is the data point. If we assume little red dots are just galaxies, we see it gets it's really pushing the theoretical limit. I'm not saying we are breaking lambda CDM with those SCD fit stellar mass, but it's true that the star formation history is uncomfortably early and efficient. Okay, now what if we just put in AGN? That will solve the overmassive galaxy problem. Because you can imagine if we put in AGN, it's gonna decrease the stellar mass. So this is a fiducial model of the AGN galaxy composite. So we put in AGN. This is a highly dust-reddened AGN. And we still expand the UV and the Balmer break with the light from host galaxy. This has a nice feature that we have a wavelength-dependent contributions of AGN and starlight. So where we see broad lines, we know it's an AGN, and where we see Balmer break, we span with a galaxy. We also have some morphological analysis suggesting that they are slightly resolved in the UV and totally unresolved in the longer wavelength band. So this also supports this composite view. However, this interpretation does not come without any problems. One of the most critical is that if they are black holes, they are not normal black holes. What I mean by this, the first thing we can do is to put them on those black hole mass versus stellar mass plane. Those are the local relations. Usually we expect the black hole mass and stellar mass relationship very tight. The galaxy and its central black hole just go through their major life events together, right? They just grow together. So the relation is very tight. But here, this is where the data points lie if we assume they are composite of AGN galaxies. So this is like 2 orders of magnitude above the local relation. You may have heard the phrase we're finding overmassive black holes. This is one of the examples. However, I have to say that both axes are highly uncertain. We get the black hole mass, assuming the 20-year-old scaling relations from H alpha. This only works at the local universe. There's no reason to think that they still work in those redshift 6 or 7. And also decomposing the stellar and the AGN line is also very challenging. So take it with a grain of salt. But there are some papers trying to say we are seeing overmassive black holes. And well, now since what I'm talking about, they are unusual black holes. I will show you my favorite example. This is a little red dot at redshift 3.1. We call it a big red dot for obvious reasons. We can use for PSF here. I resisted to put this silly name in the paper, but
you add another keyword to NASA.
well, yeah, that would be perfect. Yeah, so this is super bright. Even if we compare to the larger cosmos field, it's just unusually bright, which means we have very good photometric measurement across all those bands. And we did very detailed morphological modeling. It's really unresolved at long wavelengths and slightly extended at shorter wavelengths. So this also sort of gives us the idea that there's some intrinsic size changes of the source. Given that, we take the fiducial as the galaxy and the AGN decomposition model. Again, this is the same model. We expand the UV from host and optical emitting infrared from AGN. Well, this source I mentioned is at redshift 3.1. The good part of being at a slightly lower redshift is we can have mirror that samples to the very long wavelengths. This is very interesting for AGN because this is region where we expect to see a bright torus. Now, let me remind you why we think we should be seeing bright torus. Because, well, this is typical AGN. This is just the Vandenberg, the SDSS stack. It's very blue. Now, to make this blue AGN to match the optical continuum shape of little red dot, usually is we put in a lot of dust. The AV is like over 3. Now, just by a pure energy conservation sort of argument, when all those light in the UV and Earth optical are absorbed, they have to be re-emitted somewhere in the infrared. And in terms of the standard AGN interpretation, we should be seeing a super bright torus. However, this is not what we see. It sort of flattens out, right? If it's an AGN torus, it should be like super bright in this. This means it just really, it's really strange that we're not seeing any hot dust. This also is covered in one of those Chandra D fields. So we look for X-ray. We see no X-ray detections. So there's 2 signatures of standard AGNs. One is hot dusty torus, and the other is X-ray emission. Both of them are lacking in this source. Then without X-ray or hot dusty torus, what kind of AGNs are we even talk about, right? So yeah, then now adding more to this puzzle is the ionization properties of the little red dots. So this is what I've been thinking about most recently. Is well, if we know that in standard photoionization models, the H alpha equivalence can be roughly seen as a ionizing photon counter, meaning larger H alpha would mean more hydrogen ionizing photons. The relation is not perfect, but it's a very good photon count. The little red dots lies here. The y-axis is equivalent of H alpha, and this is ionization. This is indication of the number of hydrogen ionizing photons. The little red dots are here. This is just one of my favorite sources. They overall have larger H alpha compared to the SDSS AGNs. Now, what this means is if just purely based on H alpha, this means the intrinsic ionizing spectrum of those little red dots have to be a very hard ionizing spectrum. The standard ionizing spectrum of AGN is just a power law. So now, in order to get such large H alpha equivalence, It also comes with a lot of hard ionizing photons, which means we have a clear prediction that we should be seeing strong higher ionization lines as well. Well, can we find any higher ionization lines? One of them is helium-2 in the rest optical. It turns out to be surprisingly weak. So this is region lined by standard AGNs, and my favorite little dot. You see, compared to the large H alpha, the helium-2 open width is surprisingly weak. Now, if we accept this standard AGN like ionizing sources, it means a peculiar turnover at the helium-2 ionizing potential. This is not all like any standard AGN models. Well, if you do BPT sort of biratio diagnosis, this may be more familiar to you. This is H2 over H beta, helium-2 over H beta is N2 over H alpha. The standard is this agent here. We have upper limit in N2 because H alpha is so strong. Even with super deep medium res, we cannot decompose. But still, it lies, this little dot lies securely in the star forming region, meaning the ionizing spectrum is injury soft. But does this line ratio diagnosis still work? If we suddenly put the little red dot or whatever powering the central engine inside a growing dense hydrogen ball. This is the sort of the popular theory now on little red dots is we put agent or things inside a cocoon of dense gas. This is popular because it can explain the brown lines, also the Balmer break. So that's like the theory that can explain most of the observational signatures. Well, does this still work? If we look at the line ratios, the answer is not quite. So you can this is in the less dense gas. This is denser gas where we usually use it to expand the little red dots. The different SVD shape, the predicted line ratios start to overlap, meaning the diagnosis powers of those line ratios start to be less certain if we just put it inside a cocoon of gas. But are there any ways to really know the intrinsic ionizing spectrum of little red dots? Here's actually some hope. So this is just me trying to do Claudia models. What you are seeing here is just I've input sort of an AGN, SCD or whatever, and then let it just pass through the dense gas. We see here this is the innermost part of the gas cocoon. And as it goes redder, meaning the lines get propagate further into the gas. Now, the problem with H alpha is it flips into absorption first because the optical depths to the hydrogen is just so large, it becomes absorption first. And then as it propagates through the gas, we see emissions. This means the connections between the H alpha and the intrinsic ionizing spectrum gets lost if the ionizing source is behind a dense gas cocoon. The line is just more sensitive to the gas physics rather than the intrinsic properties. But the helium-2, you see, it's mostly produced in the outer edge. Oh, sorry, not the outer edge, the inner edge, because the ionizing potential of the helium-2 is larger, meaning the optical depth is thinner compared to those Balmer lines, meaning it can still trace the internal or the central engines of the little red dots. We can use this, try to see if we can see anything meaningful about the intrinsic properties of those sources. So this is the parameter space we want. On the x-axis, this is the helium-2 equivalent width. On the y-axis, is the defining feature of little red dot is this red optical continuum color. The parameters we want is here because the little dot has low helium-2 equivalent width, but a very red optical color. Those are the model predictions if we just assume a standard AGN SCD. The models can never enter this region of the parameter space.
Dust dependent. I mean, certainly the optical continuum slope be affected by the dust or impacted by the dust.
Right. We do not put in any dust here because the lack of mirror highly suggests that we're not looking at AV greater than 1 sort of dust.
Right, but would that not, that doesn't get you anywhere near where you need to be? Even half a magnitude or something?
You have it can if we invoke a somewhat steep dust law. It's going to be steeper than the common ones.
Okay, so you have to do something to get.
Yeah. But it can get up here.
Yeah. Okay.
But this is just assume dust-free agent SED. What can work is we put a little bit of stars in this dense hydrogen. So the stars has intrinsically softer ionizing spectrum. So now you can imagine we are sort of stacking a hard ionizing spectrum on top of it with a softer ionizing spectrum for stars. So with that, we can go to this red and also low helium to equivalent with parameter space. Physically, I mean, this is also plausible because neutral hydrogen, if we think about it, it's highly conductive for star formation. It's hard to imagine a ball of hydrogen just sit there doing nothing. And they can preferentially form massive stars. So that's one way to get out of this. Yeah, there are many things we need to do in order to establish this, but this is one possibility that can give observation consistent. Okay, so let me just finish with a bit of summaries. I think we're about the time. What my expertise is really in the modeling part, and the Webb space telescope is very exciting in this perspective because it's pushing the limits of all the existing models can address. Those are a few of the important questions I've been wondering about. So what are little red dots? Is there light from stars, from black holes, or something where there a glowing hydrogen ball of gas? What are the new observations we can propose to clearly distinguish those different scenarios or models? And then is the first star formation really the unifying explanations for the luminous ultra-high redshift galaxies and those lagging galaxies? And if so, can we really get robust constraints from those large, well-selected surveys? One thing I didn't really talk about is there are many modeling uncertainties in the SED field. It's gonna be a talk on its own because there are many fundamental assumptions we have to make in those SED models. And finally, it's really the tip of the iceberg. Currently, we are only in the middle of year 4 of Webb. It's only looking much less than 1% of the total sky. So maybe there's more surprising discoveries in the later years. And on that note, I will stop here. Thank you.
So it isn't really surprising to me that the typical AGN SED doesn't work here, or ionizing SED doesn't work in the cocoon scenario, because I don't know why you would why there would be a normal accretion disk in that case, especially if it's like a super Eddington rate. So I want to know what's the status of okay, what does the SED that would come off of an advection dominated flow or a super Eddington flow, is that being compared to what might match that a little better, the helium results?
Yes, so I'm certainly not an expert in super Eddington AGNs, but there are papers that propose super Eddington can solve many puzzles in little red dots, not only to expand the weak in the hot dusty torrents and also the weak in X-ray emissions. Yeah, but I think it's a promising model.
That was actually my question. Would that be consistent with the lack of X-ray in that case?
It would also be consistent with the lack of variability, which is why I like it. But yes, it would. You expect less X-rays because
less it goes.
Yeah, I mean, yeah, and you have horrible column extinction for the X-rays, but also the old model of the X-rays come from upscattered, accretion disk radiation in the torus. What's the torus in this case? There isn't one, right? So yeah, I think that makes a lot of sense.
Yes, I use the standard agent because it's such a exploratory model. So it's nice to have something that we really know well. And
Well, and it's cool that you can rule it out. I mean, like you're saying,
Right, yeah,
it's
and like
unlikely.
standard
So
AGN,
that's, yeah.
Does this hold up with some of the low redshift work that I know we only had 30 minutes earlier, but I was just reminded, like I know we Fan's group has done some of these low redshift analogs of LRDs. I'm trying to remember if any of them showed the strength of the Balmer break. We really use this as analogies or not. And if the answer is yes, can we delve deeper into those to figure out what the conditions are?
Yes, the most convincing one is the one, the egg, the redshift
Yeah, the egg.
one from SDSS. It's the most convincing one because they have spectra and we sort of see the V shape. But because it's from ground, the UV part, they only have a little bit of UV coverage. So it's hard to tell whether it's really upturned. And when we get to this lower redshift, it's also hard to tell whether it's a host galaxy contaminations or really the intrinsic light from say scatter. Yeah.
All right, it's just hard. All right.
Yeah.
So I was a little confused on what you mean by robust. I think there was a slide where you talked about using like data prior to more robust. So, sorry, could you like clarify a little bit what you mean there?
Oh, by robust. It's just the data were not in the lycodomic region, meaning there's multimodal solutions when we fit the models to those data. But by putting in those more observational motivated priors, we can know which solution to be downweighted. For example, the probability of finding, say, a 10 to the 11 solar mass galaxy at redshift 10 should be much lower than finding it at redshift 3. Right. So even though the data we can have statistical equivalent fits, by putting in those physics, we know which solutions to downweight, and that's what I mean by more robust.
I see. One other question. So, what samplers are you using to? You put a new prior in, and then you use the sampler. So the sample is posterior.
Yes. For that is dynasty. It's a nested sampler.
So is this like a metropolis within Gibbs sampler? Is that what
No, it's a nested sampler. It's like MCMC, but just it has pieces. They try to piece in the prior space. So in principle, it can catch the multimodal distributions better, but it's still not perfect.
How do you know how long to run it so it's working well?
The nice thing about a nested sampler is it has well-defined convergence criteria. So you can tell it calculates a convergence criteria, and then you can tell this is the place I want it to stop. It's very much unlike MCMC, where you need to manually check whether it converges or not. Yeah, it basically trying to sample along the Lyco space, and then internally it calculates the evidence. It tries to maximize the evidence.
Oh, so it is like an evidence lower bound type of thing?
Sort of, yes.
Can I ask one more question? Sorry. So you're using a prior, but you're putting data involved in it. Is this right? So you're using data to inform the prior. Is this right?
Oh, I mean, data-driven is how we constructed those priors is based on good observational studies.
Right.
Yeah, for example.
So are you actually putting data in the prior?
Not data, but how we think the universe evolved.
I see. Why am I not? Have you ever thought about putting data in the prior?
What do you mean putting data?
Use a distribution prior that maybe use data, possibly some observations.
I understand the data
Okay, no,
part.
sorry, never mind. That's okay. Thank you.
It's from younger folks in the room. Old people have been dominating. The younger folks.
You did not specify.
So young at heart. Logically young.
Call me immature. You want?
It means that you penalize, you said by default it fits some continuous non-bursty star formation history, and later you penalize the continuous emergence so you get some more bursty star formation history? How exactly do you penalize that?
Oh, it's really the priors. So the continued prior. So the prior is on the ratios of the star, the mass formed in different beings. The continuity prior just allows the ratio between those star formation rates in different beings to be like a student T distribution centered 0. So it favors continuous star formation histories. And the bursty star formation histories, we just widen the student T distribution, so it just more drastic changes between different beings.
I'll let us question.
It's very fast. We're already over the hour.
None of my questions. We'll see. We'll see if the answer is fast. I guess I'm curious about the burstiness because I was wondering, well, if you have situations where the star formation history is very smooth, would the burstier prior favor more bursty star formations of that? How do you tell? My question is, would you rule out a bursty star formation history in the case the star formation history was smooth? Is the data sufficient to overcome that? Like, this is the problem with outshining.
Yes, that's a good question that I do not have a quick answer for.
Discussion hour.
Yes, okay, good.
Yeah.
All right. Well, thank you for taking it.